Section 5.3, we're still looking at how to calculate volumes of solids, but this is another technique called cylindrical shells. So let's first take a look at what a cylindrical shell is and how we're going to use it to help us find volume. So I want you to think of like the middle of a roll of toilet paper, the cardboard center, as a cylindrical shell, so it's hollow in the middle. Now those are thin, but they still have some thickness to it. I'm kind of exaggerating on the thickness here, but this is essentially what a cylindrical shell is going to look like. And what we're going to do, imagine just cutting down, if you're standing the center of the roll of paper towel upwards, and you're going to just slice it right down the side of it, and then open it up. It's going to start to look like, and lay it flat, it's going to look like a rectangular piece. So this is what it would look like. Again, I'm exaggerating the thickness of it. But essentially, what the sides will kind of equate to here is the distance around, which is the circumference, turns into this part here. So if you were to unroll it and lay it flat, that's our circumference, which is equal to 2 pi r. But the radius here is actually from the center over, and I'm actually going to call that x. So really circumference is going to become 2 pi x. Now the height of the cylinder is the height that's over here. So I'll call that h. Sometimes it could just be referred to as y or f of x, however high that we're reaching up here. And then this thickness, call that d of x. And then that's this part right here. So if you recall, that volume is equal to length, which is indicated in the green line, the width, which is blue, times the height, which I have here in red. So that's how we're going to find the volume of this rectangular slice that comes from a cylindrical shell. But applying calculus here, let's first rewrite it this way. Let's say that volume is going to be, the length here is really the 2 pi x. The width is the dx. I'll put that in at the end. And then the height is really y. So this is our length times our height times our width. Now translating this into calculus, because we're going to have a series of these, the volume is going to be the integral from a to b of 2 pi x. And instead of y, I'm going to use f of x. And then dx. So this is going to be the formula that we're going to use, and it's a little bit more straightforward. Like with the washer, we had to find the area of the outer circle and then the area of the inner circle, and that was a lot of work to do. So this could simplify our problems a little bit. I just want to show you a little animation to show you, because my drawings are not going to do this justice. So I just want to take you through a little animation. And even before I show you that, I should have had this in the other video, but the last couple examples from section 5.2, where we had cross sections that I told you, kind of imagine them coming up through the floor. This is what we're looking at here. So these are all kind of like laying the coordinate plane flat on the floor, and then we have a series of squares or equilateral triangles or semicircles popping up, and then that's what we were doing. We were finding the area of each little cross section and then turning it into an integral to help us find the volume. But these were the shapes that we were looking at. All right, now for this one, let me get this out of the way, but what this is, the problem is saying, is to find the volume of a solid formed by rotating about the y-axis, the region bounded by y equals x squared and y equals the square root of x. So this is just a rough sketch, but they put this into a computer program that eventually takes you through what a cylindrical shell is going to look like, and essentially what we're going to be drawing here. So in this section, what we're doing, instead of shading the entire region here, we are just going to look at a little cross section that the cylindrical shell is going to kind of pop out of. Now, anytime we go to draw this cross section, we always want it to be parallel to whatever we're revolving the area around. So because it says we're rotating about the y-axis, we want to draw a little section here that's parallel to the y-axis. If we were rotating this around the x-axis, we would draw a horizontal little rectangle here as the start of the shell. So let me skip to, okay, so here it is in a nice three-dimensional figure, and they start with this little section. And then what's going to happen, let me just continue playing this here. imagine a cylindrical shell coming up out of it. So that is what one cylindrical shell is going to look like. But next, they're going to draw a series of these, and we're going to get the full figure here in its entire volume that's also going to be shown. All right, so now these are just an infinite number of little cross sections where the shells are going to come out, and then we see the full three-dimensional figure, and then that's what's going to circulate. So this is eventually what we're going to be finding the volume of. All right, but it's this formula right here that we're going to be focused on. Let's go ahead and take a look at our first example. Here we want to find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. Now this was the example that I was using throughout section 5.2, part 2. So go ahead and pause the video if you need to copy this down and get your coordinate plane started. All right, so both of these are going to intersect at 0, y equals 0 and y equals 1. So this will be the line y equals x. And then remember we had y equals x squared, which would still be from here to here. Remember how we went over a half and then just up a fourth? So that's what this section is going to be. So in order to start the cylindrical shell, we are just going to have a little sliver, little rectangle start here. And again, if I were to just kind of do a mirror image on this side, so just to show you that copied over there. And then we would get the cylindrical shell forming right here. I'm not going to draw too much, but that's where the shell would kind of go around. So what we're going to have to do is figure out what f of x is going to equal here, or the height rather. So in this case, the height is just the distance between the two curves. And the distance between is just going to be the top minus the bottom. So our height here is just going to be x minus x squared. So our volume we're going to write as the integral. We're just going from 0 to 1, because all of these shells would start going from x equals 0 to x equals 1. And then we'll have 2 pi x times our f of x, or the height of our shell that's right here, which is just x minus x squared, and then dx. So a little bit quicker, a little more simple to set this up. We could pull the 2 pi out in front. We can have the integral from 0 to 1. We can distribute the x, so we'll get x squared minus x cubed dx. And then just proceed to evaluate this integral. So we'll have x cubed over 3 minus x to the 4th over 4 from x equals 0 to 1. Substitute the 1 in first, so we'll get 1/3 minus 1/4, technically minus a 0 next. Common denominator of 12, so we could say 4/12 minus 3/12. So we're going to get 2 pi times 1/12. So 2 pi over 12 is the same as just pi over 6 cubic units. Now again, this is just another way to find this. It's not saying it's the only way. This is just another technique. Sometimes it's going to be the simplest out of all three. Other times looking at it as just revolving the area could work as well. And determining, do we have a washer or a circular disc. All right, go ahead and copy this example down. Here we're going to find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals the square root of x from y equals 0 to y equals 1. So notice here it told us our y value, so we have to do this with respect to y. So if I go to graph, there's only one curve here, y equals the square root of x. So the square root of 0 is 0, square root of 1 is 1. But this would be the top half of a sideways parabola, so it's going to start to look like this. Also, we know if we are at 1/4, square root of 1/4 is going to be 1/2. And then I could kind of copy it down here. And then sort of draw this. So if you notice, we're going from y equals 0 to y equals 1. And since we're revolving this around the x-axis, the little rectangle I'm going to start to draw for my cylindrical shell has to be parallel. Sometimes we joke and just say, play on words here, para-shell. So we know we're going to use the cylindrical shell method as long as the shell starts, wherever it starts has to be parallel to wherever we're revolving this around. So we're going to start it right here. So if I were to make a copy of that on the other side, this is where we're going to rotate, and then this is where I would draw that circular part. So that would just be one cylindrical shell. So we have to figure out the pieces here. So in this case, our radius, which is going to start from the middle of the shell and go up this way, that's going to be y. That's going to be our y value. So we'll just say the radius is the y value. And now the height of the shell is going to be from here to here. So in this case, because it is horizontal, we want to go rightmost graph minus left. Well, this dashed line that I have here is really the line, sorry, x equals 1. And then this curve right here that I have in green is y equals the square root of x, but I need to solve this for x in terms of y, so x is going to equal y squared. So right minus left, so the height is going to be 1 minus y squared. So now when we go to set this up, we're going to have the volume is equal to the integral from y equals 0 to y equals 1. 2 pi times our radius, which is y, times, in this case, is going to be our f of y, because x is equal to f of y, because we're writing x in terms of y. So that's just going to be 1 minus y squared times dy. So again, we can move the 2 pi out in front times the integral from y equals 0 to y equals 1, distribute the y. So we're going to get y minus y cubed dy, and then we can go from there. So evaluating this, we're going to get a y squared over 2 minus y to the 4th over 4, again from y equals 0 to y equals 1. So we're going to get a 1/2 minus 1/4, technically minus a 0. So we'll get, there's really 2/4 minus 1/4. So we're going to get a 1/4 here. So we end up getting pi over 2 cubic units. All right, let's just take a look at one more example. Go ahead and copy this down. Here we're going to find the volume of the solid obtained by rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. So what I first want to do is I'm going to draw a dashed line here going through x, or 2 on the x-axis. So that's going to be the line we're going to revolve this around. Now in order to graph y equals x minus x squared, let's go ahead and find the x-intercepts here. So let's set that equal to 0. Factor out an x, so we're going to get a 1 minus x. Set both of these equal to 0. So x equals 0, and then x equals 1. So we're looking at x-intercepts here and here. Now I would like to know, let's say maybe 1/2. So let's do at x equals 1/2, y is going to equal 1/2 minus, I'm looking right up here, 1/2 minus 1/2 squared, so 1/4, which will just give us a 1/4. So I'm actually going to change how I'm numbering my y-axis. I want to make this look a little bit larger. All right, so my 1/4 is going to be right here. So we're also bounded by y equals 0, which is just the x-axis. So I know that's why I don't have to go down any lower, but this is sort of we know it's a parabola, so it's going to look like this. So if I'm reflecting it over this purple dashed line here of x equals 2, it's just going to map over to here. Now again, I want to draw the part that the shell is going to come out from has to be parallel to the line that we're rotating about. So it's going to be a vertical section. Just kind of draw it here, which is going to map over to here. So this is where my shell is going to start to rotate. Just looking like that. All right, so when we go to figure out the radius, let's go back to the original curve. So my radius of this shell that I have drawn in here, again, we want to go right minus left. So the radius is going to equal 2 minus whatever x value I'm looking at. So 2 minus whatever x value we are dealing with here. And then my height is just going to be my function, which is x minus x squared. So now as I go to write out the volume, the integral here, again, we're just going from x equals 0 to x equals 1 because all of the shells are going to start over here. So it's going to be 2 pi times my radius, which is 2 minus x. And this is only because we're revolving this around a line that is not the x or y axis. And then times the height, which is x minus x squared dx. All right, so let's go ahead and put that 2 pi out in front times the integral from x equals 0 to x equals 1. I'm going to go ahead and multiply those two together. So 2 times x is going to give me a 2x. 2 times a negative x squared is a negative 2x squared. Inside here, we're going to get another minus an x squared, and then we're going to get a plus x cubed. Combine some like terms. So I'm going to go ahead and put the x cubed first. Minus 2x, I'm sorry, minus 3x squared now. We can combine those. And then plus 2x dx. Go ahead and take the antiderivative now of each term. So we should get x to the 4th over 4. This will just become a minus x cubed because we'll get minus 3x cubed over 3, so just a minus x cubed. And then we'll get a 2x squared over 2, so it's just going to be x squared. So substituting in the 1, we're going to get a 1/4 minus 1 plus 1, and then technically minus a 0. So we get a 2 pi times 1/4, which again is pi over 2 cubic units. All right, so I just wanted to introduce you to some examples, walk you through some examples of using this technique as well. So that was section 5.3. The little bit of a last section that I'm going to go over, section 5.5, it is a very short section, just over a couple problems, not dealing with volumes of anything. So you might enjoy that a little bit more after going through these few sections of volumes and area between curves.